So I will just start with a small introduction, presenting the topic, presenting the team, and how it's gonna work, and then we're gonna have the battle itself. So to click here. So this is the main event. Thank you for joining us. So we're gonna have first a quick introduction by your host. So it's me, Luc Doucet. I will present the topic. Then I will present the today's teams. And then we're going to have a lucky draw. So we will decide which team starts presenting their arguments. So I will use an app on my phone. This is the maybe unbiased way to decide. Then each team going to have 20 to 30 minutes to present their case. And after that, so after each team presented their case, we going to have questions from the audience. So to make things easy, please ask your question in the chat and with your name, full name, then I can read your name and ask the question to the different teams. And then we're gonna have concluding remarks for each team about the topic, about today's discussion. Let's start with, okay, here, small introduction. So plate tectonics. Why do we want to talk about plate tectonics and why do we have this battle today? So basically, we had in the 60s what we call the plate tectonics revolutions. So it was a paradigm shift. So basically, the plate tectonics theory explain what we observe on the oceanic seafloor. So when we have the spreading rate, the different ages on the part of each ocean ridge, so the magnetic stripe as well. So on this recent paper by Setan et al. 2021, so you see this is the reconstruction of the age of the seafloor, and we see the oceanic spreading ridge here, and this has been explained by plate tectonics. And plate tectonics, it's something very important because it can explain a lot of different processes. And using plate tectonics, we have been able to reconstruct Earth's history, what happened in the past. On this is an animation from a full plate reconstruction by Meredith et al. 2021 in Earth Science Review. So it's a small animation showing the breakup of Pangaea, the well-known supercontinent, and the paradigm shift of the plate tectonics allows us to understand Pangaea and how it evolved from the supercontinent Pangaea until the configuration we know today. So this is just the small animation. So we start in 200 million years, and we have the plates, drifting, and we have spreading ridge, we have subduction zone, we have collisions, we have rifting, we have all these phenomenon we can observe now in the geological record that can be explained by plate tectonics. This is how plate tectonics has been very, very important in the earth science. And actually plate tectonics is like the papers by Einstein for physics. There is before and after this theory. So we see that now we have the continent moving toward the more present day configuration for the continent. Just to continue a bit with plate tectonics, this is the time scale for the Earth represented as a clock, so a 24-hour clock. So if you see my here, I think you can see we start here at 0, right? And we are moving toward that direction on this clock, and you see the different period of time. So we have the Hadean, we have the Archean, we have the Proterozoic, and then you have the Phanerozoic with every different steps in the Earth's evolution when we have the appearance of the first single-cell eukaryotes, the multicellular eukaryotes, animals, colonization of the land, etc., etc. And one of the main questions we are having in the discussion is, in the community, sorry, about, so we know we have plate tectonics now, and the question is, when does it start? So do we have plate tectonics from the early days of the Earth, or it appears later in the Earth history? And this is an ongoing debate, and if you go in the literature, you're going to find countless papers about this topic. This is why it's a very hot topic right now in earth science, and we need to discuss about it to present the evidence for the early appearance of plate tectonics or the late or everything in between. So today we're going to have two teams to discuss the different topics about plate tectonics. The first team, what I call the team Emergence, is a team made by Professor Stern and Professor Guerilla versus the team of uniformitarianism, per se, by Professor Ross Mitchell and Associate Professor Richard Palin. So a bit an introduction about the contestant for today. So in the team emergence, we have Professor Stan, as I say, Professor of Geoscience at the University of Texas at Dallas, studying the evolution of the continental crust and approached by tectonics, chemical and isotopic studies of modern processes in ancient products. He works in arc system of the Western Pacific, Neo-Proterozoic crust of the Northeast Africa and Arabia, China and Iran, for example. In this team, we have also Teras Garia, which is adjunct professor for geodynamics, analytical and numerical modeling of geological and planetary processes in the Department of Earth Science at ETH in Zurich since 2010. And his research focused on plate tectonics, geodynamics, planetary processes, as well as numerical geodynamic modeling. Against this team, we're gonna have Ross Mitchell, professor at the Institute of Geology and Geophysics in the Chinese Academy of Science. And his interest is how planets works in general, I would say. His area of expertise includes palomagnetism, cyclostratigraphy, supercontinent, true polar wonder, and Earth history. And his research aims to discover the governing dynamics of the supercontinental cycles by taking a system theory approach. With Professor Mitchell, we're gonna have Richard Palin, Associate Professor of Petrology at the Department of Earth Science at the University of Oxford. And his major research includes process or technical-oriented studies concerning fluid rocks melt interaction, change in metamorphic products and processes through geological time, and the geology of other rocky bodies in our solar system and beyond. This is for the formal introduction. So now we can proceed to the battle itself. So why people are joining us today. So now it's time for the lucky draw. So who's going to start? So I would just use my app between the emergence team and uniformitarianism and waiting. And this is the uniformitarianism team that starts. I'm not sure if you can see. Yeah, I didn't cheat. Are good?
We believe you.
Excellent. So you're gonna have 20 to 30 minutes to present your argument, and I guess Richard, you can share your screen.
Share now. Yep.
Oh, I need to unshare. Stop sharing first.
You can see mine or not?
Yes, we can.
Okay. Thank you for the introduction. Thank you for the invitation to take part in this. And also thank you to Taras and Bob and Ross for agreeing to take part. It's going to be a lot of fun, I think. Ross and I are probably going to talk for about 20 minutes. We like to spend some time at the end with questions. So we've got about 20 slides. And I'll start so we're not wasting any more time. So we were on Team Uniformitarianism. We're going to argue that tectonics started early and give some evidence for that. Early itself is a strange word. Some people's version of early might be the Hadean. Some people's version of early might be the late or the middle or even the early Archean itself. It's complicated, but we'll go into a time chart in a second. Central to this question is how you would define plate tectonics, how you would recognize it in the geological record. And we thought we'd stick up a nice slide here, which is from one of Talas's papers, Fisher and Geringer, on one research 2016. It nicely shows through his geodynamic modeling that there's transitions between mobile lid plate tectonic regimes and stagnant lid regimes. Here, we've used, well, I've chosen to use a definition by a paper by Weller and Lenardic, where they say that it's the relative velocities of the lids to the underlying mantle that helps you to define which end of that spectrum that you're on. So the lithosphere obviously is different from the asthenosphere. You can distinguish it in many ways. Composition, rheology, dominant mode of heat flow. The stagnant lid regime would be where you have the lid itself moving very slowly, perhaps imperceptibly slowly compared to the mantle below. And a mobile lid, plate tectonics, would be where the lid is moving significantly faster. How much faster is the question you need to answer. It's a transitional feature in nature. Could be 10 times, 100 times, maybe 1,000 times is a bit extreme, but you see the point here. And it's true that many forms of stagnant lid exist. So what we're looking for and what we're going to argue for is evidence that the plates have moved at some point in the geological past. So this harks back to the question of what does early mean? We have this generic diagram, these time charts that you see in many, many papers. And this one's one of our recent review papers, but they all show similar data. Some people argue it's extremely early. We have Hadean onsets proposed by some authors. A lot of authors propose different times in the Archean, and this is where I stand as well, and Russ would stand with me, I hope, being on the same team. Some people in the past have proposed quite late onsets, whether their opinions have changed or not. I mean, that's something I can't talk on their behalf of. But I thought I'd splash this up to give you an indication of the range in ages, the range in time. So why is it so hard to try and understand when plate tectonics began? So because we're arguing for uniformitarianistic principles, that subduction, convergent margin processes have operated for a decent amount of time. Early, in our perspective, would be, say, at least since 3GA, at least since the Meso-Archean. That would be when we're saying that would be the oldest time you could recognize some of these features. And you can break down these lines of evidence in many ways. In my past papers, in my past reviews, I've used 4 different types. Modeling can be one way to make inferences on whether subduction can occur. Geodynamic versus petrological modeling. You can look at geochemistry, isotopic signatures. You can look at tectonic arguments, styles of deformation, this kind of stuff. And petrology would be the 4th main pillar that I would argue for. And petrology is my thing, so I'm going to talk a bit about petrology. We will very, very briefly talk about petrology, geochemistry, and tectonic evidence. I'm not going to touch on modeling based on who we're arguing against, who's much more knowledgeable on that front than I am. And this has to be extremely, extremely brief because each one of these could take on a complete lecture series if you wanted. So we've chosen some key papers or some key exhibits in our case we would like to put forward. The first exhibit would be diamonds and the evidence that diamonds themselves and their inclusion suites can contain. So exhibit A is diamonds. So if you're going to ask where can diamonds form within the Earth, different types of lithosphere, oceanic, non-cratonic continental, and cratonic continental lithosphere, only cold, thick continental lithosphere, cratonic lithosphere, will reach the depths, the pressure and temperature conditions in the Earth to form diamonds. And this is where you find them. You find them in kimberlite pipes that have erupted up through cratonic lithosphere. Now, in theory, you could form diamond at any place in the mantle if you're over the graphite diamond transition and if your oxygen fugacity is significantly reduced. But there's not enough carbon in the mantle, like in the background kind of mantle, to actually form diamond itself. So people have argued for about 220 to 250 ppm as a baseline value, and that's not enough. You would make carbon would dissolve into your iron nickel alloys, or it would make a carbonate instead. You need to add more carbon to the mantle to make diamond. And then how do you do that? So we then moved on to a seminal paper, which I'm sure everyone here is familiar with. And it's Sherry and Richardson, 2011. This is a science paper. And they looked at inclusion suites in diamonds from 5 different cratons. It's not an even distribution of diamonds from these different cratons. It's fairly weighted towards the Capval, I think. Could be wrong from memory. But they still looked at 5 cratons worldwide, and they saw common features in each. There was a sudden appearance of eclogite type inclusions in these diamonds post 3GA and before 3GA. So the diamonds that were dated at this 3GA, 3.2GA time period. Beforehand, you had peridotite-like inclusions. So no evidence of subducted or transported mafic crust into the mantle, which would eclogotize and get caught up in these diamonds. So they, in their paper, argued that 3GA was actually a significant time period. It's a tipping point in geodynamics, and they attributed this change in inclusion suites to the onset of the Wilson cycle. So subduction could be one way to transport carbon into the mantle to form these diamonds and these eclogite inclusions within. Exhibit B, onto the petrology. If you're going to identify subduction, convergent margin processes in the geological record, you would look for rocks that form exclusively in those environments. So we know that blue schists and eclogites, in particular, these 2 types of metamorphic rocks, eclogites are not unique to subduction zones, but in this case, they often form in subduction zones. Blue schists in particular is the more reliable indicator. And looking at this time chart of facies through time, you might say, oh, but wait, there's no blue schists far back, further back than 0.8 GA, 0.9 GA. So therefore, there's no evidence for subduction. But I'm going to take a slightly different tact on this exhibit to say, well, actually, the absence of blue schists in this case and eclogites in a somewhat related case is not evidence for the absence of subduction. Some people might be familiar with this work I put out in the past. We put out this paper in Nature Geoscience in 2016, where we related secular cooling of the mantle to a change in oceanic crust composition through time. The hotter Archean mantle produced an oceanic crust that was more magnesium-rich than today's moor. And then we did some phase petrology using calculated phase equilibria. And we showed that actually the blue schists that you look for in Phanerozoic belts, you can't form the same mineral assemblages from a high magnesium-rich basalt, even if you subduct it to blue schist facies conditions. And this is quite a strong argument, if I do say so myself, for saying that you can't use the lack of rocks like blue schists past this age of about 0.9 as evidence for the absence of subduction. Eclogites are a separate kind of matter. We recently put forward a new hypothesis to deal with eclogites in 2021 paper. It's just come out in Geoscience Frontiers. I would just direct you to that if you want to read more. There's not time to cover everything now. Exhibit C would be basalt trace element geochemistry. So we're sticking with the petrology, the geochemistry. Ross will do some more tectonics in a second. Basalt is extremely abundant on the Earth's surface today and makes up the entire surface of the ocean floor. And Ken Condi's work in the past has shown that it's actually quite prevalent in the geological record too. And you would use, or you would like to use, the trace element geochemistry compositional characteristics of basalt in modern day terrains to try and work out where the basalt formed. Did it form in a mid-ocean ridge? Did it form in a back arc basin? Did it form on a continental flood basalt like the Deccan Treps? And there's distinguishing characteristics, trace element ratios you can use to tell these apart. So what happens if you apply these ratios to basalts back through geological time? So I personally like this paper by Ferns et al. In Geoscience Frontiers. There was one in the same year in Gondwana Research that touches on similar themes. Either is worth a read, I would say to the audience. And they applied these trace element ratio discrimination diagrams to moderately metamorphosed, weakly metamorphosed basalts and greenstone belts and ophiolite complexes that pop up in the geological record. And they span 0 to almost 4,000 million years old. So you have a whole range of Earth history preserved in these rocks. So these are mobile trace element ratios and quite easily distinguish arc and non-arc geodynamic settings. And it's the arcs you would look for evidence of subduction and plate motion in the past. So to quickly summarize Ferns' results, they analyzed a large number of samples within a large number of complexes, over 230 individual complexes. And they found that over 85% of the Archean population had arc-like signatures. So because time is very short, I'm going to have to summarize my points already. So summary of exhibits A, B, and C. Well, first off, we should say, maybe it's often hard to define what plate tectonics is or what evidence you would look for. And this was mentioned as a comment by Tim in the chat before we even started. But the petrology, the geochemistry, and the isotopes, which I didn't touch on, but there's 3 lines of evidence here that we would argue, Ross and I, to say that plate tectonics, or at least some kind of subduction-driven plate motion, has been going on for quite a long time. I'll pass this over to Ross now.
Thanks, Richard. So I just want to start, sorry, with a lot of text here, but my kind of understanding of the 2 philosophies of the 2 teams here, I want to make clear that I think, and Richard and I agree on this, both are viable. That doesn't mean we come to the same conclusion, but that does mean that you have to listen to both of us. So on the left is kind of Richard and I's uniformitarian approach, and on the right is Bob and Taurus's kind of late emergence. And hypothesis testing, many of you know from Karl Popper's influence on science. People argue that you can't really prove a hypothesis like a proof in geometry. You can only reject hypotheses. So if you find 100 white ducks instead of 10 white ducks, that still doesn't offer more of a proof that all ducks are white. But if you find one black duck, you can reject that idea. So this comes to what in statistics calls the null hypothesis, that there's no significant difference between two populations of data. In the case of the debate today, those two data populations are modern and ancient geodynamics. Uniformitarianism, which everyone knows, present is the key to the past. Uniformitarianism is a great null hypothesis, and it's exactly that. There's no significant difference between modern and ancient geodynamics. And so the question then becomes, from this approach, can we reject the null hypothesis of plate tectonics? And if so, at what age? And something I'll point out later is that we don't think this is inconsistent with secular change. Now, the approach our opponents will be taking, also viable but different, is kind of inspired by Occam's razor. The simplest or the least complex approach is better. And they ask the question, is plate tectonics required to explain Earth's early geologic record? Can we explain the Archean record without plate tectonics? I shouldn't mention this, but Richard was on a paper, as well as Tim Johnson's paper, that kind of point out that arc-like signatures in Archean TTG don't necessarily have had to have formed in arcs. So they take that Occam's razor approach. Secular change has influenced geology, obviously, in the last few decades. Earth used to be a lot hotter, not only because it had more heat-producing elements, it also had more accretionary heat. And the geologic record looks different. Archean was dominated by TTG. TTG does form today, but it's quite rare. And our opponents had a great article where they point out this uniformitarianism trap. And I think it's good. They basically say, even if you can't reject this null hypothesis, that shouldn't stifle you from entertaining alternative hypotheses. I don't think the various hypotheses that are being entertained, are necessarily warranted until we can better reject the null hypothesis. But the thought is out there. These two philosophies come to us from very early on. Charles Lyell, founder of geology with uniformitarianism, Lord Kelvin, developing this idea of evolutionism, using the cooling rate of the Earth to calculate the age of the Earth. However wrong Kelvin was, his influence of getting geologists to think about secular change was clearly ahead of its time. And Rich and I are kind of more on the left, and Bob and Tara is a little bit more on the right. And we like to think of science as this two-sided battle. But of course, in reality, nature doesn't care about how humans do science. The reality is probably somewhere in the middle. And that's kind of interestingly where Charles Darwin was in space and in time. Charles Darwin obviously embraced uniformitarianism by studying the finches and Galapagos today, but he also embraced the fossil record, acknowledging secular change through Earth history. Now, Bob Stern, I don't know whether he'll mention this. Bob Stern, wrote some very provocative papers in 2007, arguing for Neo-Proterozoic onset of plate tectonics. And, however, his views might have changed at the time. It was quite important and maybe warranted because we didn't have a well-developed Paleoproterozoic supercontinent. This audience, I don't need to explain, but since then, we have absolutely firm evidence. We may argue about the configuration. We have firm evidence of a Paleoproterozoic supercontinent, whether you call it Columbia or Nuna. So, at least that old view of Neoproterozoic, completely unviable. And for someone as myself doing my PhD on a Paleoproterozoic supercontinent at the time, I couldn't believe we were talking about the Neoproterozoic. So hopefully we can get a little more serious with the constraints we now have. I do want to point out our opponents may try to make some argument about local versus global, and plate tectonics has to be a global network. The phrase plate tectonic network is a modified phrase. referring to present day Earth. Subduction, I don't know how you have subduction if you don't have plate tectonics. Whether that subduction was global, okay, that can be debated, and that should be debated. The first evidence for global subduction not only is the supercontinent itself, but the Science Advances paper, where we show with seismology that there's an interconnected network of subduction zones. So it kind of, instead of a semantic debate, let's get serious about when local versus global, how that evolves. And Dave Bercovici, Yannick Ricard have a really neat way of talking about the accumulation of plate boundaries. And just by analogy, adolescence, your formative years, is a different thing from birth. So just because Earth is changing as we do in our teenage years, that doesn't mean that we weren't born earlier. Going farther back in time, let's find more deeper evidence for plate tectonics with Archean cratonization. Two papers last year in Nature, both modeling how to form thick lithospheric keels of cratons. Both of them have subduction zones. So these are models. Maybe it's possible to form thick Archean lithospheric keels without subduction and this relamination, but that's not what the current models show. And from the geologic record that most people in this audience will know, Archean cratonization is as old as Pilbara, that 2.9 billion years, but it is notably diachronous. Okay, we know this very well. It took hundreds and hundreds and hundreds of millions of years until all the Archean cratons formed. Maybe this is accumulation of plate boundaries. That still doesn't mean that plate tectonics wasn't operational when that process began. As a paleomagnetist, I have to shine a light on this very important recent paper by Roger Fu at Harvard and his student Alec Brenner. They got some hard-fought paleomagnetic data from the honey eater basalts in the Pilbara craton, almost 3.2 billion years. And they showed paleomagnetic apparent polar wander. Pilbara was moving, and they compare it to data from Kopval. Kopval was moving. Unfortunately, differential motion or relative motion is the hallmark of plate tectonics. During my thesis, we proved that for the supercontinent Columbia. We haven't proven that for this age yet, but to their credit, the authors point out it could be plate motion if we assume that the paleomagnetic motion is plate motion, or it could be true polar wander, which is not relative motion, but wholesale motion. And my little cartoon depicts what TPW is. So, plate motion versus TPW, a little bit unclear, but a first promising step. And if their assumption is right, that it's plate motion, it's interestingly around the same age as the eclogitic diamonds Richard mentioned. Just very briefly, if we go farther back in time, earlier Archean and Hadean, the geologic record is very scant. And this is when geochemistry has entered the fray. Jung Karnaga has done some great work with recent students showing consistency with different geochemical systems. I'll mainly talk about argon. Argon's released into the atmosphere. One of the best ways to contribute to argon in the atmosphere is generating continental crust, which is potassium rich, which decays to argon. And in order to explain the argon degassing history, they really have to have rapid crustal growth in the Hadean or even early Archean. The reason their net crustal growth curve goes flat after that is there might have been new crust generated. There obviously was, but the same rate of crustal recycling kept the net growth no higher. Now, the main ambiguity here, and this is not one of our Richards and I's exhibit, the main ambiguity here is that recycling could just be delamination of crust. They prefer plate tectonics because to get the argon, you need the potassium, that's most done in felsic crust, and most felsic crust forms in plate tectonic settings. So they have an argument, but let's leave it there. And just to drive this point home, that uniformitarianism does not need to deny secular change. The principles of plate tectonics don't change just because you change the parameters of, say, mantle viscosity, mantle temperature. Okay, and we haven't proven an Archean supercontinent. The evidence we've published in Liu Yibo's geology paper actually shows that there probably wasn't an Archean supercontinent, maybe separated supercratons. But how did those supercratons form? My interpretation in the recent Nature Reviews paper is that Earth might have evolved from very small wavelength convective cells to larger wavelength, and that could have quarantined, if you will, these supercratons from each other. But just because you don't form a supercontinent doesn't mean plate tectonics didn't exist. And so here's just my summary slide. I tried to put together some of the evidence that both Richard and I presented going forward in time. The battle today, I look forward to what our opponents have to say, but I think as a field, we need to, a different approach maybe in the future is coming up with an emergence consensus, a consensus model that we can all test. Consensuses may ultimately be wrong or be revised, but it helps to know what everyone in our field is trying to test instead of changing definitions. Definition, I have local to regional to global. If you're specific about what your data actually inform, if Alan Nutman has evidence from Greenland, he's proving uniformitarianism, but he's proving it for Greenland. Okay, if you have diamonds from 5 cratons, you are getting more regional, but it's still not global. But once you're getting to Archean cratonization, which is nearly global to definitely supercontinent, I think we can get a refined consensus argument that we can argue about. So thanks for listening. I know it's supposed to be a battle, but I think that these two, evolutionism, uniformitarianism, are both viable. We need to appreciate each other's approaches, and they're not necessarily mutually exclusive. So thanks to Luke for organizing this. Thanks to our opponents. And thanks to Richard for fruitful, really lively discussions. I want to publish more stuff on this and be like the rest of you guys. So thanks for listening.
Okay, cool, very cool. So we had the first team presenting their case very nicely, actually. So Ross, if you can just, yes, perfect. So Bob and Tara, so which one of you want to start? To the emergence team?
I will start. Because I have less day and almost no data at all.
Excellent. So now it's time for the emergence team with Teras starting.
So I hope you can see my screen, right?
Perfect.
Okay, cool. So so our answer to the question is, did plate tectonics started early? Is no. And unfortunately, I should acknowledge that, in fact, I drifted to this idea through years of research, and I was forced to do it by two main arguments that I will try to present to you. One is more philosophical, another one is related to professional activity, doing models. And if we think about emergence and emergence of plate tectonic, then we should also unavoidably think about something that was before plate tectonic. So, for example, here there is a chicken, and then there is an egg which does not look like a chicken. So, and then there is something in between, a gap in between, gap in knowledge. So if we believe something was different before plate tectonic began, we should try to reconcile all steps in between these kind of two phenomena. And we should acknowledge that our data, they have some fundamental gaps. So, and one of the very important issues that I would like to bring to your attention, which is, one of my arguments, is that we have very limited and unavoidably limited data availability for reconstructing geodynamics of the Earth. Geodynamics is reconstructing of the Earth's history of both interior and surface through geological time. And if we believe that interior can be characterized simply by these depths, So then we have at least two-dimensional diagram to be covered by data to be able to reconstruct history of the Earth on the basis of data. And such data are in principle not available to us. There are no data points at all depths at all times that are available for our interpretation. So simply because we have knowledge about Earth's interior for the present moment of time, thanks to geophysical data, but this knowledge does not go further than probably a few decades ago. Then we have, of course, surface observation and plate tectonic reconstructions. Some of them go further than the others, but in general, you know, our surface record is quite limited. And in addition, rocks record that is available to us is generated from rocks which are formed at relatively small depths. So no mantle xenoliths formed deeper than 300 kilometers. So we, in principle, have this area empty. So we have to interpret phenomena and processes having fundamental void in the availability of data. Then we have to compensate it with something. And what we use intuition. So, and this intuition can be potentially erroneous. It's dangerous to use intuition under such circumstances because our intuition is trained by the domain where we have most of the data. We have most of the data for present day plate tectonics. Therefore, we are doomed to overstretch well-defined and successful paradigm of plate tectonics back in geological time. So these dangers should be recognized and you should take it into account. Every time you want to stretch plate tectonic back in geological time, you should admit that you are doing this for the reason that your intuition is calibrated on plate tectonics. So it's such a successful paradigm that it's spoiling. So this uniformitarian actualism principle is a good thing when we speak about, for example, validity of physical laws back in geological time. But if egg does not look like a chicken, then, you know, fully basing, you know, our knowledge on how chicken moves and flies and so on will not give us much idea how an egg was looking like. So I was showing these slides many times and saying that, you know, knowing thousands of chicken, how they move, how they, you know, communicate with each other and so on, does not help us to imagine how an egg was looking like, because egg simply does not look like a chicken. So, and this is the point. So when we will try to operate within this diagram of Earth geodynamics, what we will tend to do all the time. So we will take this knowledge and then propagate it back in time and try to interpret all data by, you know, adjusting our chicken to the data. So we will flatten it, we will, you know, change definitions, we will rotate it, and we'll always try to, you know, stay within the same successful paradigm. So this is why I would like to be more restrictive in terms of defining what plate tectonic is. So first of all, I would like to say that plate tectonic is presence of the mosaic of rigid plates separated by weak plate boundaries. And this plate mosaic does not appear, you know, instantaneously. It can be established through geological time by some, for example, inheritance and damage processes. So this mosaic should be in place. So if there is no such rigid plate mosaics with weak plate boundaries, then it's not plate tectonic. So second point is then spreading is driven and compensated by subduction in modern style plate tectonic. And this is only possible if we have rigid oceanic plate interior. So spreading can only exist because subduction happens, and subduction can only exist because new oceanic plates are born by spreading. So then driving forces are then slab pull is the major force and ridge push. So, but once again, important is spreading and subduction are interconnected and, you know, compensate each other. So another point that long-term uninterrupted continued subduction is possible, and then continued long slabs can be created in the Earth's interior, which we, you know, image with mantle seismic tomography or Benioff zone position. So, and this is also coming from present day observation, and this is what I would like to also put into plate tectonics definition. We need global network of subduction zones. So local subduction does not mean plate tectonic, because otherwise Venus has plate tectonics. So some of the Venus corona structure are interpreted on the basis of comparison with detailed models as perhaps local circular subduction or subduction-like process. It does not last for very long, but it develops, and then we have subduction. Moreover, some people, we see here continental-like domains with thick crust and high topography, oceanic-like domains with thin crust and low topography. And some of these domains are set in motions, as for example shown in this Harris and Bidar paper, 2015 for Lakshmi Planum. So there are some felsic domes which are likely present in evidence for continental-like crust. But this is all in a completely non-plate tectonic framework. So here it was suggested that continental-like domains are moved by plate currents, but there is no global network of rigid plates separated by weak boundaries, and subduction is only operating locally. So to me, this is not plate tectonics, this is completely different style. So this is why I would like to be very restrictive in my definition. So on the other hand, another line of evidence that I would like to bring is what models are telling us about what style of tectonics is to expect in the past. So based on composition of magmatic rocks generated in the mantle, we know that mantle was hotter in the past, 150 to 250 degrees hotter than at present, and plumes are even more hot. So, and then what models were telling us through years of exercise is that classical plate tectonic features and this relationship that I brought to your attention, they disappear or break apart, and then new tectonomagmatic processes, they develop in models. So when we were starting this exercise with Elena Sizo, we were just taking most successful subduction models and trying to increase simply mantle temperature. And what I was expecting then, something will change, but not much. We will still see the same relationship because temperature dependence of viscosity is exponential, so it's difficult to get rid of any rigidity. But in fact, what occurred is that as soon as we started to reach some temperature above present 150, 175 degree, because of the presence of these red melts patches everywhere, so melts percolate through the lithosphere in all places, lithosphere become weaker, it can jam, and it does not form nice continuous subduction zones. And even high increase in the mantle temperature produce just chaos, which does not look at all like subduction and plate tectonics, and it was called no subduction regime. And then further exercises with this regime show it that we start lots of plumes and drips, which are destroying this nice plate tectonic relationship. Plus 175, 150 degrees, we see lots of things that we would like to call more Venusian type tectonics, vertical tectonics. Also horizontal motions are not excluded, and even further increase. So we see this plume drip tectonics or squishy lid tectonics. And what are consequences of this very mobile regime, Venus-like regime of tectonics? We have weak deformable plates. As a result, we can have ultra slow oceanic spreading without subduction because the loss of the newly created material at mid-ocean ridges is compensated by the loss of material by means of eclogitic drips or delamination processes. So once again, we lose this connectivity between spreading and subduction. Then subduction can become local in both time and space. So very short-lived episodes of subduction are possible. So they are still very important for this. But once again, if we have local subduction on Venus, it does not mean that Venus has plate tectonics. If we have some horizontal motions as in this model, it does not mean that we have plate tectonics. So at least to me, with my, I should admit, a relatively restrictive definition of plate tectonic. So, and lots of things are emerging, which we do not observe at present day, such as domes and keel structures, delamination processes, eclogitic drips, which are sometimes connected to this dome and keel structure, sometimes not, because these are two different levels of activity, mantle activity and crustal activity. So everything looks very different from what we expected initially when we tried to entertain such models. Simply hot mantle temperature does not like and does not agree with plate tectonics for the reason that more melts is generated, melts are percolating through the crust and lithosphere, weakening it, and in general, higher temperature implies more weakening, and then it stabilizes other types of tectonics. Even if we force subduction locally, as in this paper, we see some other interesting phenomena that are not present in the present day plate tectonics and can probably explain formation of cratonic keels at this hot non-plate tectonic mobile environment. So if we can have local subduction, for example, then due to the presence of sublithospheric depleted mantle, which is not present now because depleted mantle is fully incorporated into the oceanic lithosphere. We can have this backflow, which can, in principle, explain localized in time development of cratonic keels, which are layered both in terms of chemical and mineralogical composition. So this is why I think, we should take into account that we have an emergence phenomenon in between, early days where we had likely plume lit or squishy lit tectonics, similar to what we have on Venus now, which is not plate tectonic, but still very mobile environment. So it's not stagnant lit. Then we had some transition. The question is when, how, probably multiple times. And then we have these recent days, classical modern style plate tectonic. So currently, and models are pushing me always forward in time to set the limit for modern style plate tectonic. Currently, I'm more or less believing that the beginning of this was in between 1 giga-years and 0.5 giga-years. And more arguments on that will be presented by Bob Stern next to me. So to me, the question is, when and how and why this transition happened. Perhaps it was extended in time, but to me, likely this modern style of plate tectonic was established very late in the history, mainly due to the secular cooling of the mantle when all these complexities, they were deactivated that we see for Venusian type plume lit tectonics. Thank you for your attention, and I give word to Bob now.
All right. Thank you, Taras. You eloquently made the argument that we need to consider strongly the physical controls on planetary convection. Now I'd like to build on that and talk about the geologic record. So we all agree that Earth is unique among the silicate bodies of the solar system, the actively convecting silicate bodies of the solar system, and that the other three have some different style that ranges from Eo's heat pipe to Venus's many plumes and drips to Mars sluggish, a few good plumes and drips. And we all agree that Earth's mantle, its mantle potential temperature has been decreasing. We're not sure how much it's decreased, but that decrease in temperature caused emergent behavior in Earth's tectonic regime. And this is the way I see Earth history over the last 4.5 billion years. And you'll be interested to see that, yes, there's something like protoplate tectonics at 2 billion years. So that is not a point of contention. But what happened between that time and today, and what happened before that time is, and I'd like to concentrate on those issues. So remind you that Taras's very nice diagram, that as we go back in time, we have less and less geologic information, and we can basically abandon hope of direct geophysical information from the deep Earth. But let's work our way back slowly, and let's not jump back to the Archean where the record is more incomplete. Let's work our way back through the Phanerozoic into the Neoproterozoic and into the Mesoproterozoic carefully. And then we can build on those consensuses possibly to advance our understanding of earlier Earth history. So just to remind you when the Neoproterozoic and Mesoproterozoic were, this is over 1 billion years or almost a quarter of Earth history. And we focus on the tectonics of this time period because it's easier to figure out than the tectonic regimes of earlier times. Next. So briefly review the geologic evidence that plate tectonics began in the Neoproterozoic. The 3 plate tectonic indicators, rocks and minerals that can only form by plate tectonic processes today. And those are the seafloor spreading and subduction initiation indicators, Ophelites, subduction generated rocks, and continental collision rocks. And you can find these publications online. So the seafloor spreading and subduction initiation indicator are Ophelites. And In spite of what the previous speakers have said, the presence of Archean Ophelites is very controversial, and those who publish those things are usually embarrassed by what they say later. There are some Paleoproterozoic ones at this time of interest. The good Ophelites are Neoproterozoic and younger. The subduction indicators, including blue schists, which have already been commented on, are limited to Neoproterozoic and younger time. Lawsonite, which is a very interesting mineral that only forms in subduction zones, is also limited to Neoproterozoic and younger time. Jadetite, which is a gemstone of interest to the economic geologists, is only limited to Phanerozoic time. And the collision indicators of ultra-high pressure metamorphic rocks and the gemstone ruby, those are also limited to Neoproterozoic time. And ruby, there's a few that are a little bit older, but by and large, they're also limited to younger time. So you can make any one of these go away, but as more and more evidence is collected, it becomes clearer and clearer that the geologic record for Neoproterozoic and younger time is fundamentally different than earlier time, with a possible exception of about 2 billion years ago. So if plate tectonics began in Neoproterozoic time, Earth's tectonic regime in Mesoproterozoic time must have been some kind of single lid, was it? So if it was, then its products must look different in many ways from the products of Neoproterozoic and Phanerozoic time. Do they? And the answer is yes. So if we look at some single lid indicators, which I published in GSA Today in December, we can look at two dry magma indicators, A-type granites and anorthosites. And they are remarkably concentrated in Mesoproterozoic time, shown here in the flesh color, and remarkably absent from younger time. Another interesting feature of single lid tectonic regimes is that the mantle lithosphere and the crust above it should heat up because it is being insulated and heat is building up. And in fact, the Mesoproterozoic is a time when the thermobarometric indicators, shown here in degrees centigrade per gigapascal, in metamorphic minerals, increased, and then since that time has been decreasing. And then finally, the evidence of passive continental margins, which require plate tectonics to form, are absent from the Mesoproterozoic. They are abundant, increasingly abundant in Neoproterozoic and more recent time. They are interestingly evidence of them at around 2 billion years. And if we just simply divide Bradley's data into those with less confidence and more confidence, we see that with the exception of maybe one here at 1 billion year, there's nothing that looks like a convincing passive continental margin that formed in the 600 million years of Mesoproterozoic time. Now, the economic geologists are interested in this controversy too, because ore deposits are things that they can mine and make careers out of and get rich over. And so important things like orogenic gold, which are concentrated in recent times, and interestingly enough in the Archean, and porphyry coppers, which are concentrated in modern times and controversially older, are missing from the Mesoproterozoic. Instead, we have a group of very unusual ore deposits, the Corunna magnetite apatite, the iron oxide copper gold, and the ilmenite anorthosites, ore deposits that don't form at another time in Earth history. So strictly from an economic point of view, there's no question that the Mesoproterozoic was fundamentally different than what we see in Neoproterozoic and younger time. So again, there are no plate tectonic indicators preserved in Mesoproterozoic rocks. So the evidence, both the positive evidence from these different kinds of rocks and ore deposits that form in Mesoproterozoic, as well as the negative evidence, the absence of the plate tectonic indicators, makes any thoughtful person say something fundamentally different happened and it's most consistent with interpretation that the Mesoproterozoic was a very interesting time of single lid. Now, a couple more points. If there was this transition from single lid Mesoproterozoic into Neoproterozoic and Phanerozoic plate tectonics, that must have severely disrupted the Earth system. And I want to talk about two of them. One of them is a climate system. We know that the Neoproterozoic was a time of climate crisis, unparalleled in Earth history. It's called Snowball Earth. And there are many different interpretations for what caused that. But the simplest one was that the Earth was responding to a trauma in this conversion of the solid Earth system. So we can see that in the carbon isotope record, which has been excellently developed back through time. The Mesoproterozoic isn't as well defined as we would like it to be, but the Neoproterozoic, there's no question that the Earth's climate system went crazy. These glaciations, these carbon isotope fluctuations, and this could be telling us something about how long it took to make that transition from the Mesoproterozoic single lid to modern plate tectonics. Now, biological evolution is the big question. How did this transition from single lid to plate tectonics change biological evolution? And this is something that Taras and I and others at ETH are very interested in. But we know from the life record that life took off in the Neoproterozoic about this time. This is when all kinds of eukaryotes, animals, the fossil record starts at the end of the Neoproterozoic. How would the transition from single lid to plate tectonics affected biological evolution? Well, by affecting 5 key processes that link life and the solid Earth. First, the increased nutrient supply. As a result of collisions and rifting, there would be more relief and weathering, increasing the supply of key elements like iron and phosphorus into the oceans where life was taking off. The increased oxygenation of atmosphere and ocean during a Neoproterozoic oxygenation event due to enhanced photosynthetic activity, probably related to the increased nutrient supply. There would have been the climate amelioration due to CO2 drawdown as a result of plate tectonics. After that was part of what was happening with Snowball Earth. There would have been increased habitat formation and destruction due to the Wilson cycle. Evolution happens when you get isolation and differential stress, and that would have been happening as a result of the continental shelves moving around, forming and moving around. And then there would have been sustained but gentle pressure from environmental changes due to tectonics. So I've talked a bit about this in a 13.5 minute video. We post all of our talks on the UTD GSS YouTube channel. I invite you to take a look at them at your leisure. So I think the geologic record speaks eloquently to what happened during the transition from Mesoproterozoic to Neoproterozoic time. That of course the earlier times are important, but until we resolve the first quarter of Earth history, we're not ready to embark on examining the earlier times. And thank you for your attention. Thank you for inviting us to this fascinating discussion, and I look forward to your questions.
Yeah, thank you, everyone. Thank you for the teams for presenting their argument and for, I would say, respect the timing. Very good. And thank you very much. So now I think we can move to the question from the audience. But before that, I was just wondering if we can try something new. So I was wondering if if you have like the two teams have a question for each other, we can start like one question, either it's from Ross or from Richard to Bob and Taras, and the other way around, just to have like a bit of one question, one response, one question, one response, and then go to the audience. What do you think?
Yeah,
sure.
we can go for it, to warm up auditorium, and we can go.
Yeah, exactly. That's exactly what
each other. It's a good idea. Yeah.
Yeah, that's what.
Two good teams, so why not to try?
Well, I got a quick question. I'm just going to close the screen then. Sorry, it's loud outside. Taras presented very well, saying how hot and mantle produces a different style of geodynamics, etc. And you have different styles of subduction, shallower with weaker plates. Maybe they fall apart. Maybe they're not as strong as in the modern day. But we were saying that even if it's a different style of subduction, it still is an indication of plate motion. Plates are still moving around because subduction zones and ridges concurrently are allowing them to shift across the Earth's surface. So, I mean, do you have a comment on that? Just the fact that it might be.
It's exactly the thing that I wanted to bring, for discussion. So how restrictive is our definition for plate tectonics? But to me, the exploration should really try to compare Earth and Venus, because for Venus, there is a documented feature such as, rudimentary plate motions. So, but still Venus does not show any good mosaic of rigid plates separated by weak plate boundaries. And to me, I was forced in a way to sharpen my definition of plate tectonics because of this difference. So until we agree that we would like to discriminate Earth and Venus as non-plate tectonic planet and plate tectonic planet, we, can bring some local arguments, but, local motions does not mean, presence of the global plate mosaic. And also it was repeatedly suggested that on Venus we have this global local subduction, which may even lead in the end to global overturn. But it's still not plate mosaic and not really modern plate tectonic. This is why, I prefer to keep more restrictive definition of plate tectonics, to have discrimination between Earth and Venus. Otherwise, they will be the same. They will the same tell that we have plate tectonics on both of them. And I somehow have difficulties to agree with that.
Good. So,
Taras,
Taras,
we'd invite a question from the other team, I'm sure.
Yeah. So, Taras or Bob, if you have a question for Ross or Richard.
Well, I'm happy to ask one about diamonds. I don't think diamonds are useful, or their inclusions are useful indicators of plate tectonics. And for that, indicators of transfer of solid material from the surface to depth is not an indicator of plate tectonics. It is an indicator of vertical transfer of material, but there's ways to do that. And I think kimberlites are a more useful indicator of plate tectonics because they require a huge buildup of fluids, which a late start to plate tectonic explains why kimberlites, not diamonds, kimberlites are so young. So what do you think about that?
What I think about that is that you didn't mention your alternative mechanism, which I assume is delamination, and delamination will not form diamonds. We need surface materials going, you said vertically, but we need surface materials going deep. Delamination, yes, is another vertical process, and yes, delamination happens on Earth today, but delamination will never take surface materials, which is required for diamond formation.
No, but there's no problem to have an anti-plume that enchains the entire surface material and takes it down. I don't think delamination is the only way that vertical motions can happen in a non-plate tectonic Earth. You see the synformal nature of Archean greenstone belts, which implies that something is sucking them down, and that material could have gone vertically down into the mantle. So it's not just
know what an anti-plume is.
Sometimes see this.
So yeah, Ross, if you want to respond to that.
I don't know what an anti-plume is, but it sounds a lot like a subduction zone, which is specifically different from delamination.
Yeah, I was showing these eclogitic tubes which are forming, on the continuation of some of these dome and keel structures. So they're not one-to-one correlated, but what you see, in fact, dome and keels, they're propagating greenstone materials into the lower crust. Sometimes this material can become partially molten and give rise to TTG formation, but sometimes it travels laterally, and then because of perturbation of Mocha boundary, it can form eclogitic drifts. So it's not a straight way from the surface to the mantle, but it kind of indirect way, it can still preserve some volatiles. At least this can be entertained. So there are quite efficient recycling of material in this type of stuff.
I agree
Russ?
with that, Taras, but it's predicated on the assumption that dome and keel is not plate tectonics. Tim Kuski could say a lot more about this and has a paper coming out soon, but he basically shows, modern batholiths in Sierra Nevada that preserve very similar structures that you see in dome and keel. Just because there's two directions of folding and you get a dome when you weather it doesn't mean it's not plate tectonics. And the Pilbury example has really been overplayed.
Okay, so I think now there is some questions just piling up in the chat. So thank you guys for asking question, answered questions. So I have a question from Susoblan Neogi. Sorry for pronunciation. Pardon my French. So to the team Emergence, what about the Mesoproterozoic mobile belt around the globe? The PT evolution of these belts are identical and clearly indicates role of plate tectonics. What do you think, guys, about it? Bob and Taras.
So I'll take that one, Taras. Mobile belts imply deformation. Deformation does not require plate tectonics. It's that simple.
Straightforward.
Okay.
So you have Russ, you want to add something?
Well, we don't really want to get ensnared in arguing about the Mesoproterozoic, since Bob conceded Paleoproterozoic plate tectonics. I would say that there's this pretty profound reorganization from Colombia to Rodinia. And there's wholesale motion well documented for supercontinent Colombia during the exact interval that Bob's proposing. I'm interested why there's few Ophelites preserved. I'm interested why there's few passive margins. To the point of the discussion today, Richard, points out, I guess we're arguing mainly Archean versus versus Paleoproterozoic.
I have to comment. I have to disagree with that most vehemently. We do want to get ensnared in the Mesoproterozoic. If we assume that Earth went from non-plate tectonics to plate tectonics in a single move, as many community people want to do, we've made a mistake. Earth's tectonic regime has emerged, and we should open our minds to the possibility that Earth may have had multiple episodes of plate tectonics and multiple single lid tectonics. We need to work from the thing that we are most confident about back in time slowly. To jump to the Archean is a mistake. Let's focus on the Mesoproterozoic and the Neoproterozoic.
Okay, but there's a difference between a single lid and two plates. So a supercontinent is a two-plate system. And if you have intraoceanic subduction, you're not going to preserve Ophelites. You really need to prove that there's a two-plate, there's a one-plate system, not a two.
Okay, can I just, sorry. Just try to get the debate, on the trade. So I have just a question. So it's just more a philosophical question for you, Bob and Taras. So uniformitarianism is the principle that say what you observe today occur in the past, right? That's my understanding.
Yes, correct.
So
yes.
It's not just a question, but in using the record for the metamorphic rocks like the blue schist, the lawsonite, etc. So is using the uniformitarianism principle, saying that if we see blue schist, we should see plate tectonics as it is now, right? So it's quite interesting to using uniformitarianism to demonstrate emergence, right? But in Ross and Richard talks, what they say is that they assume that Earth's change, right? They just assume that plate tectonics occurred, so where was working, but because the Earth was different, so the record is different. So how Bob, do you comment on that? So what is your view about the changing of, like if you can't have blue schist for example, in the Archean or even in Mesoproterozoic, what would you?
Well, I would like to step in here, Bob, if I can, for a minute, as a field mapper in the Archean for 40 years. So I will say something. I work in the Mesozoic and Cenozoic and active tectonics and the Archean. And like in mapping southern Alaska accretionary margin, there are no eclogites. There are 3 outcrops of blue cysts, okay, for 2,000 kilometers. And what we have is gray wackies and little tiny slices of accreted ocean plate stratigraphy. Two decent Ophelites, but almost just little scraps of a little basalt here and basalt there, intruded by TTG magmas and stuff like that. So a lot of these things that are called so-called indicators of plate tectonics are actually very rare. And I have heard nobody talk about the structural geology of plate margins in here. Very few people are talking about the actual geology of the Archean cratons, or about the size of what's preserved or the preservational bias, okay? So it's an impossible question to find a Eo-Archean globally linked plate boundary if the cratons are only 100 or 200 kilometers across that are preserved. But we can find structural, geochemical, and magnetic evidence that might be consistent with that. And if we use like what Richard Pollan and Bob Stern said, the null hypothesis, and we say it is consistent with the operation of horizontal motions of plates with a change of geothermal gradients that change certain things, like the metamorphic rocks, like the chemistry of the basalts that come out, they get more mafic, and about the biological and the oxygen isotopes, etc. Then we can test, going backwards, how did plate tectonics change with time, instead of making up all these models about, well, it went, I have a model and it went stagnant lid and went this way and this way because I can make it on the computer. And those are great and they're all possible.
Okay, so I think, sorry,
so try it.
Sorry, Tim. Yeah, so if you can, yeah, if Bob, you want to reply, so to my question, and also that.
Can you rephrase the question?
Yeah, sorry. So the question
probably wants to respond too.
No, yeah. So the question would be: so Richard and Ross are assuming like plate tectonics occurred throughout, let's say, for a long time, but then because the Earth was different, maybe hotter, maybe for this kind of stuff. So plate tectonics, like the record is different. So the record for plate tectonics change through time.
Okay. So okay, we have 2 chickens. One of them has 4 legs and a long trunk. The other one has feathers and 2 legs. And those 2 chickens are both chickens, right?
I don't know.
mean, how can two things that appear differently be the same thing? So, and Taras, jump in here because you're the poultry specialist.
Yeah. Potentially, once again, do we want to confuse Earth and Venus or we don't? So if we do want to confuse Earth and Venus as the same style, tectonic style planets, then of course, we can apply uniformitarianism because Earth was likely operating more similar to Venus in the geological past. But if we believe that these are 2 global different tectonic styles, then we have to put some boundaries. So, and by itself, plate motions do not imply global plate tectonics in modern sense, because plate motions can be accommodated by jamming of this weak lead, also including creation of some, collisional zones, as was suggested for Venus, for example, in front of the Lakshmi planum. We can have local subduction because of plume-lithospheric interactions. So not global network of subduction zones, but some local circular subduction zones, and so on. So to me, the distinction is really here. So if we want to confuse Earth and Venus, or we are fine with doing that, then no problem. So plate tectonics was, since very early times, because in the early times, Earth was operating like Venus. If we do not want to confuse them, then we have to, find out when we have changed from one style to another style. So okay. This is what
we don't want to. I love your point, Taras. We don't want to confuse them, but Richard can explain why some of the evidence that people use based on making plate tectonics have to be the same as it occurs in the Phanerozoic could be biased. If you just briefly explain, the blue schists.
Okay, so I think it's almost 1 hour and a half. So I will just give the yeah, the time flies. Interesting discussion. So
well, I'll just say read the paper then.
no. That's what I'm saying.
It's the quickest way.
No. I want each team to have the time for their concluding remarks, and I would like to ask each team to try a little exercise. So, for example, Ross and Richard, if you want to start with your concluding remarks. So, what would you do? What would be like the null hypothesis for for early plate tectonics? What evidence would convince you that plate tectonics emerge?
If people just want to entertain more questions than do concluding statements, to me, I might find that more interesting, getting more voices.
We can continue discussions. Yeah, probably.
Okay, so see, people want to ask questions and stuff. So
you have a question,
I think we just.
Ken? Hopefully he'd tell us about our key and greenstone belts.
Well, I would like to ask a very simple-minded question, if I may.
Go for it.
And I think it's a little in continuation of your request for the two teams to sum up about what will convince Russ that plate tectonics was late, and what would convince Bob and Taras that it was early. To me, it seems that you are discussing indicators for some processes, but you keep discussing parts of the whole question. But we have not heard how you define plate tectonics. I mean, Taras has hinted at it. There must be plates, and they should be forming a global system that is moving, something like this. But it would be nice to know what do you actually regard as the evidence that there was plate tectonics? What defines plate tectonics? Before we begin to discuss the various indicators, which can be explained in various ways, and then we can continue the discussion, which is of course very interesting, but we do not answer the question by doing this.
Well,
So
Taras is
my simple-minded question is, what defines plate tectonics for the two teams?
Taras did a good explanation. It's convection driven by the sinking of lithospheric plates in subduction zones aided by ridge push, but that's plate tectonics. And it's a global network, a fractal nature, and that pretty much covers it, doesn't it, Taras?
Yeah, exactly. And then also important point is that spreading is compensated by subduction, or subduction is compensated by spreading because of rigidity of plates. So, and this is more or less the restrictive definition that I would like to entertain to discriminate between Earth and Venus.
Okay, our definition, my definition, Rich can mention his, plate tectonics is a mode of mantle convection. Okay, it is a mode that involves the surface in convection. That does not happen in a stagnant lid. Okay, that doesn't mean it has to be global. I have no idea where that concept came from. We addressed that head on in terms of the accumulation of plate boundaries, the development of a plate tectonic network. So simply stated, it's a mode of plate tectonic convection that involves the surface.
And if I may comment on the two answers, I think it explains quite a lot of the debate that has been going on here, that the two definitions are not the same, and therefore the answers will also not be the same. So in this regard, I think it has been very, very useful with this debate, because if we begin to agree that we do not agree about the definitions, then there's room for progress. I don't know so much about the early plate tectonics. I know a bit about the lithosphere, and we had the same discussion about what is the lithosphere for the last 30 or 40 years, and we still don't agree because it depends on the method we are using. And here it's evident that if you have two different definitions, you'll never agree on when it actually started. And I think that this is a useful thing to realize. And then we can continue the discussion about what sorts of evidence we have.
Hans, maybe
Thank you, Hans. It's indeed important to spell it out.
I think that's a very, very nice conclusions for for this kind of debate.
Really is.
Yes.
You already made the same conclusion indirectly by the question you were about to formulate as a conclusive comment.
Actually, I do want an answer for my question. So yeah, Ross, let's start with Ross and Richard. What evidence to convince you that plate tectonics emerged? Ross and Richard.
Well, I would say, so Hamed asked a really good question. What drove plate tectonics to occur in the first place? The reason I think it's important for us to get beyond definitions is because there are people trying to solve that exact problem. How do you create deformation, weak zones in the lithosphere? And those people acknowledge that weak zones could have been localized and became a more global phenomenon over time. And they are interested in the time range of that. So once we can agree on not arguing about definitions anymore, I think we can provide people who are trying to answer that bigger question better constraints on when the first plate boundaries formed. That's what I'm convinced by. The Jack Hills, I'm not convinced that's a plate boundary. The argon degassing, I'm not convinced that's a plate boundary. But once you start getting to convincing evidence for, we made our case for diamonds as plate boundaries, even if it's localized, you still have a plate boundary, and that means you have plate tectonics.
Yeah, I mean, Ross and I agree on many points, so I don't want to repeat what he's just said. I mean, I would like to see evidence for the so-called independent motion of chunks of the lithosphere, the plates, across the Earth's surface at some significant speed that is faster than the rate of mantle convection. And this is why I think the Brenner article that was highlighted by Russ is very important.
Okay. Bob, Terras, what would convince you that the plate tectonics start very early?
In fact, I can spell out what was suggested on one of our other big discussions concerning the beginning of plate tectonics and the role of Meso and Neoproterozoic. So what was suggested is, if we would have somewhere evidence for long-term existing, subduction calc-alkaline arc operating through tens of millions of years and producing something that looks like what volcanic arcs are producing at present, this would be a convincing evidence that continued subduction was possible, and continued long-term subduction likely implies globally established plate network, because then you can compensate subducted material with the newly created material from the oceanic spreading. So this seems to me, one of the convincing arguments that subduction was operating or global plate tectonics was operating at that time. Because otherwise subduction itself, it can be local subduction as well as I was saying many times, as on Venus, you start by plume impingement into the lithosphere, negatively buoyant lithosphere. You have a start retreating subduction. It lasts for some period of time, then it stops, and then, nothing else happens. So this means that there is no global network of plate boundaries established and subduction dies out. So to me, this is not plate tectonics.
But for the record, Taras, you specifically invoked that mechanism to explain the initiation of plate tectonics on Earth.
Exactly, yes. Yeah, but not in a simple framework. So you first have to prepare the lead for global activation. And here I agree with you when referring to this fundamental work of Dave Berkovich and Yannick Ricard, that gradual accumulation of damage within the lithosphere is needed before we can even start this global plate mosaic to operate. And then how plate mosaic was activated, probably by the plume, because it does this activation seemingly on Venus. Perhaps when lead is ready for global action, it can do it like in Caribbean, as was suggested by Scott Wadham and Bob Stern. So stories is likely very complex.
We can agree on that.
Yeah, the comment section, the chat section is very
How
active.
many
Which is,
thousand messages do we have?
yeah,
right?
that is very cool. So you want to comment on that, Bob?
Well, I think number one, there's 2 points I'd like to make. Number one is this idea that plate tectonics began at a time and continued is rather simple-minded, that we should make our exploration much more along the lines of things may have changed frequently and for unexpected reasons, as emergent systems do. We should start thinking about Earth evolving as an emergent system. The second point I'd like to make is that if there is a major change in Earth's tectonic regime, that should have a fundamental effect on things at the surface. And so anytime when people want to see or argue for a major change in Earth's behavior, there should be some climatic and biological evidence. And of course, that record is more incomplete as we go back in time. But to separate the biological record and the climate record from the tectonic history is a fundamental mistake on our part. It's making us less interesting to the world of science. We want to be more interesting.
There's many hypotheses for how to initiate Snowball Earth that involve tectonics that have nothing to do with plate tectonics starting or restarting at that age, such as the...
It's another fortuitous occurrence.
No, not fortuitous. Well, in the framework of your hypothesis, I would argue that it's fortuitous. Yeah.
Okay. Just to comment also on comparison between Venus and the Earth and Mars. So my understanding is, so there is no plate tectonics on Venus, right? But the mantle of Venus is apparently different from Earth's mantle. So Venus is dry, right? And so how is it possible to, so it's an assumption, right? But how do we compare, two planets without plate tectonics, which are Venus and Mars, and the Earth, which has plate tectonics, but is hydrous mantle? Taras, do you?
Yeah, in principle, we had a very nice presentation today by Lena Noak. She reminded us that Venus mantle should not necessarily be very dry. It can contain water, but water is just not degassing because of the high, high atmospheric pressure, which is almost 100 times higher than on Earth. So in fact, there might be much less chemical differences in between Venus and Earth, but there are very big differences in terms of the surface temperature and in terms of atmospheric thickness and pressure. So, and composition, of course, because Venus has CO2 rich atmosphere. And as a result, if we believe that water is serving as lubricant for plate boundaries, so absence of liquid water on Venus surface is probably one of the major obstacles for making subduction to operate kind of uninterrupted on Venus, because very quickly after subduction-like processes being initiated on Venus, then they just freeze together, these plates, and subduction does not continue. So, and this is what is different between Earth and Venus, really, like surface temperature and atmospheric pressure, and absence of liquid water, which is consequences of these differences in the surface temperature and atmospheric pressure.
And I would just add, someone mentioned everything's different on Venus. It's the same size of Earth. So that's the reason why we often want to compare it. And just another thing, subduction zones are not always linear belts. You look at every ocean arc in the world, they're all curved, more or less just like the ones Taras showed on Venus.
I think Venus is great to look at as an analog for the early Earth, but yeah, I have never seen the reasoning between using it as a comparison for modern day Earth.
Well, and let's not count on early Mars. It had an ocean, so the water issue that Taras mentioned is less restrictive. There is serpentinite all along the Martian crustal dichotomy. They do have kind of ocean thin crust and high lands, thick crust. And we know very little about the early Martian history. So one thing Bob does so well, and Taras, is bringing this interplanetary perspective. But another thing, a comment on that someone said is, if we can't figure out Earth, why are we arguing about other planets? So, just different approaches. I think both of those statements have some wisdom, have an interplanetary perspective, but also, don't let every detail about comparison to other planets misguide us. Because as we've all agreed, ancient Earth could have been very like these other planets at different times in their history.
So I think there
Exactly.
is.
We like to increase our database by any means. So since we have this fundamental data restrictions, so and we are calling, no matter what is available.
So we have Ken Condi want to ask a question. So Kent, if you want to unmute. So you have your, yeah.
Actually, my comments were relevant to what Bob Stern was saying a little while ago about the Mesoproterozoic. I gave a presentation on this 2 or 3 months ago and updated many of the criteria that he used to indicate the Mesoproterozoic was a one-plate planet or a stagnant lid. And I think those criteria need to be looked at again. For instance, A-type granites, we now realize are becoming more and more recognized in the Phanerozoic, especially in Eastern Asia. We're also finding out that indeed there are passive margins that developed during that time. We have a lot of information now from paleomagnetism to indicate there was a supercontinent formed, Columbia Nuna, and that it had origins around the margin, which are very, very similar to convergent margin origins in the Phanerozoic.
Very good accretionary belts along Laurentia throughout the Mesoproterozoic.
Exactly.
In the Spheconor region.
So Bob, you want to say something or add something regarding Ken?
So all of those compilations are from the literature. They're not mine. So when a compilation is updated, say the passive margin one, that's Dwight Bradley's. When he updates that, I will use that. When Kent's exactly right about A-type granites in especially China. That compilation comes from him. I look forward to it being updated. The Northosite compilation comes from Ashwell. And when these are, be clear, these are not my compilations.
Nevertheless, you should not use outdated material, Bob.
I will use the most updated compilations that I can find in the literature. And if you know of more updated ones, please send them to me. I would appreciate
it. I'll just say, because obviously I can tune in. These compilations don't take into account the processes that we've discussed as to why these indicators may be absent.
No, of course not. These are the data. These are the data, not what is. You're absolutely right. Evidence, absence of evidence is not evidence of absence, but it's not no evidence either. And as you look at one compilation after another showing the same thing, after a while, the weight of the evidence, no, it does. It impresses some of us more than others.
It's been noted in the chat that there's a lot of Proterozoic and Archean features.
Please.
Some people in the audience will argue are reliable.
I don't.
And do not feature on some of your charts. So.
The compilations are the ones that we can find in the literature. You should please note that we're not spending a lot of time on the Archean because the Mesoproterozoic is enough of a bear to wrestle with.
Hans?
In your opinion, yeah.
Yes, in my opinion.
You're muted, Hans. I think Hans wants to...
sorry, I have another question.
Go for it.
Coming out of geophysics, having been working with seismic imaging and such things, I want to ask both teams, how do you regard the evidence that came out of seismic and seismological studies that demonstrate that collision structures known at surface can be followed through the crust into subduction-like features where we can see the structure, but we can also tell from the seismic observations that there are significant changes in the physical parameters across this subduction like structure down to at least 100 kilometers. There are very good evidence for such phenomena or such observation in southern Fennoscandia and in Canada, about 1.8 billion years old, and less convincing perhaps for Archean similar structures. How does that affect your thinking about plate tectonics? Is it possible that you bring together two completely different types of lithosphere with a structure that resembles totally modern subduction without having plates that are moving?
So let me respond to that, Hans. For the Mesoproterozoic, which profiles are you talking about?
I'm talking about the Babel profiles in Fennoscandia, and I've forgotten the names of the profile in Canada, east-west.
What age is?
There's as many as 6 profiles, and we added a new one from North China in Science Advances this year.
What age are these profiles? What age?
Sorry, there are differences in the degree of documentation. I'm talking about the two that really show distinct differences in the bulk physical properties of the lithospheric mantle. I know the best, the one from Fennoscandia, because I worked on it myself. I apologize, I cannot remember the names of the key authors for the Canadian example.
Lithoprobe and Laurentia, yeah.
Yeah, Lithoprobe.
In Canada, there's a report by John Percival about the snorkel profile and the other ones, and they show the moho offset going from, in several places, the greenstone belt.
Yeah, no, Tim, that's not, that, I'm sure that can be discussed, but I'm talking about that there are distinct differences in physical properties across a subduction-like feature. Let me just take the one from Fennoscandia. It's a change in velocity in the uppermost mantle from 7.8 to 8.2 kilometers per second. That cannot be disregarded. The temperature is approximately the same. And there is a clear indication for a shear zone that is dipping into the mantle. I think that this is very solid evidence that there must have been collision and probably also subduction related to this, to creating this structure. And there are other examples. There's one in particular, like in Canada, and there are many other examples where the evidence is less strong, let us say that, or less documented.
For Hans, I would refer to recent paper in Nature by Fabio Capitani and co-authors. They show that you can potentially create quite heterogeneous lithosphere in non-plate tectonic modes, and then there can be a lot of horizontal motions and underthrusting structures that are formed in non-plate tectonic regime. So it means that these thrusting processes, they are by themselves not an evidence of, plate tectonics, at least in the modern sense. So I can also imagine that, for example, if tectonic domains are moved by, mantle wind or mantle currents, they can collide with surrounding lithosphere, and then some underthrusting structures can form, and they can be frozen then in the lithosphere. And such imbrication processes, they were previously suggested, in a purely plate tectonic framework for the origin of cratons. But as recent works showing this can also happen in non-plate tectonic framework just due to the mantle convection and heterogeneous lithosphere with different degree of depletion and different mechanical properties.
We are almost 2 hours within the chat, so I will just probably other people have some commitments, including maybe some of our speakers. So
bedtime.
Sorry?
Bedtime.
Yeah, it's almost midnight here in Perth, so still, even though I'm very thrilled by the discussion, but I will just officially close the the session right now, and if we can stay a bit to discuss the one we are available. Okay, so I just want to say thank you everyone for joining us. I just want a round of applause for the speakers from both teams, and yeah, very nice presentation, very nice discussions. I mean, it's that's something I will change next time, having 1 hour discussion after the talks, just to put that into the into the
schedule.
Yeah.
exactly into the schedule. Yeah, because yeah, very, very cool. So I would say thank you everyone. If you want to leave, that's okay. I would say. And for those who want to discuss a bit, we can stay around for a while and then leave as it is. So thank you again. Thank you very much, and have a great day, a great night, and see you next time.